Okay, so this is 8.2. We're going to cover zero, negative, even, odd, and undefined exponents. So a lot of these are are details, except for the negative exponents. That's definitely a major idea. Okay, so Roman numeral 1, negative exponents. Okay, when you see an negative exponent, it means reciprocal. So you're going to flip it, and then it will become positive because you've put it where it belongs. One of the biggest misunderstandings about negative exponents is that they mean the number itself is negative. That's not the case. So a negative exponent is not the same thing as a negative number. So in some ways, negative exponents are a symbol that you need to move the term, flip it. In other ways, you're going to do math with it. So negative exponents are math and symbol both, which you have to kind of wrap your head around. Where it fits into what we've been doing is you can have no negative exponents in your answer. So at the end of the problem, you can carry the negative exponent through the problem, but at the end, you have to get rid of it. And that can either be a first step or a last step. Some of the examples today, I'm going to show you two ways to do the same problem that accomplishes the same thing. Now, like I said, a negative exponent is a symbol that means reciprocal, but it's also math. You can add, subtract, multiply, or divide with negative exponents. Typically, you do the add, subtracting, multiplying, and dividing first. And then when you're done, the last thing you do is move the negative. That's generally how it goes. But like I'm going to show you in a second, there's a few options that you can use. All right, we're going to start really easy and go more complicated. So a to the negative n. If a number has a negative exponent, you're going to give its reciprocal, so 1 over a, and because you've moved it, the n becomes positive. So after you move it, the power becomes positive. Okay, example 2. Let's say you've got 1 over x to the negative 2. If the negative exponent is on the bottom of the fraction, you still flip it. So my x squared would go to the top over 1. And again, the exponent would become positive because you've moved it where it belongs. Okay, example 3, we've got 4x y to the negative 2. Now, in this example, only the y is raised to the power of negative 2. So when you simplify it, the 4x stays on the top, and only the y squared moves to the bottom. Only the part that has the negative exponent. Okay, here's one I'm going to show you two ways to do it. We have 3x squared y to the 4th to the power of negative 2. Most people prefer to do the math first. So 3 is to the power of 1. Power to a power rule, keep the base, multiply the exponents. So 3 to the 1 times negative 2, which is negative 2. X to the 2 times negative 2, which is negative 4. Y to the 4 times negative 2, which is negative 8. So they get rid of the exponent, and then they move everything. So 3 squared moves to the bottom, x to the 4th moves to the bottom, y to the 8th moves to the bottom. And now there's no more negative exponent, so the only thing left to do is multiply the number out. 3 times 3 is 9. So 1 over 9, x to the 4th, y to the 8th. So that's the first way you can do this problem. You can use the negative exponent just like any other exponent, and once it's as simplified as you can get it, then move. Here's the other way. The other way to do it is to move the entire parentheses down. So 1 over, and then in parentheses, 3x squared y to the 4th. Once you move it down, it's now to the power of positive 2. So you can move that whole unit to the bottom and then distribute and then simplify. So both of those are legitimate. Okay, example 5. We're going to branch out a little bit. X to the negative 2 to the power of 0. Power to a power rule says you multiply. So you have negative 2 times 0, which is x to the 0. Now, we've already talked about a power of 0. Anything to the power of 0 is 1. Yep. So you could have like AB to the power of 0. And since the whole thing's to the power of 0, it would still equal just a 1. So that's your power of 0. Okay, last one. I'm going to give you a nifty little shortcut. Let's say you've got 4/3 to the power of negative 2. I like to do this shortcut when I have a lot of powers to deal with. This one's pretty simple, but if I have a lot of stuff going on the inside, I might just want to get rid of the negative exponent before I do anything with it. So what you can do is you can flip this 3/4, and then the exponent becomes a positive 2. Now when you distribute, because it's 3 to the 1, 4 to the 1, it's 3 to the 1 times 2, which is 2, 4 to the 1 times 2, which is 2, and that becomes 9/16. So that's one way to handle it. The other way to handle it is to distribute the negative 2 to the top and the bottom. So that would give you 4 to the negative 2 over 3 to the negative 2. And then you'd need to flip both of them because they're both negative. So your 3 squared would go up, your 4 squared would go down. And now we're right where we left off with the other one. So 2 ways to attack it. Find one that you like. All right, that is negative exponents. And then I also showed you exponent of 0. So Roman numeral 2. We're going to get into undefined values. Undefined values. Okay, undefined means there is no possible answer. There's an official abbreviation for undefined is capital U period, capital D period. So you can write it out or put UD. Saying something is undefined is not the same thing as having a solution of 0. 0 is an answer. Undefined means it can't even be calculated. Now, in algebra, there's lots of things that are undefined, but for what we're working on right now, the main thing that's undefined is if you have a 0 in the denominator. So like you have a number divided by 0. You cannot divide by 0, so it would just simply be undefined. Now you're going to run into undefined values on your worksheet, and we're just going to do one example of this. They're going to give you an expression like 1 over a minus 4, and then they're going to tell you to evaluate that expression, and they're going to give you a couple different values. Let's say a equals 1 and a equals 4. So what you're going to do is substitute the 1 in and see what you get. So when we substitute the 1 in for a, I get 1 over 1 minus 4, which is 1 over negative 3, or negative 1/3. That is defined. That's an answer. The weirdness happens when we evaluate with a equaling 4. So this time we're going to sub the 4 in. So 1 over 4 minus 4, this creates the 0. So in that case, your answer would be undefined. You would not write 1 over 0. That's part of your work. It would just be undefined, game over. All right, so that is undefined values. Roman numeral 3. We've talked about this, but I want to get it in your notes. Even and odd powers. All right, so the rule says if a negative number is raised 2. If a negative number is raised to, number 1, an even power, if it's raised to an even power, the answer will always be positive. Number 2, if a negative number is raised to an odd power, the number will always result in a negative value. All right, so let's do an example. We're going to do negative 3 to the power of 7. So you have a negative number to an odd power. Now, the reason the rule makes sense is if you have 7 negative 3s, that means you have 1, 2, 3, 4, 5, 6, 7. And the reason this works is for every 2 values, you get a positive. A negative times a negative is a positive. A negative times a negative is a positive. A negative times a negative is a positive. But because it's odd, in the end, you're always multiplying by a negative that doesn't have a partner, which is why it will be a negative 3 to the power of 7. You can pull that negative out of the parentheses and stick it out front. Okay, example 2. Negative 4 to the 4th. Again, this is now a negative number to an even value. So let's see why this works. We have 4 negative 4s. And just like the last one, a negative times a negative is a positive. So for each pair, you get a positive. Now, unlike the odd power, we don't have that spare negative at the end. So all we have is pairs of values that are going to be positives. So your answer is going to end up being positive 4 to the 4th. And then you'd probably evaluate that. So the rule makes this a whole lot easier than having to write out all those numbers. So if we take negative x to the power of 9, it's a long time to do 9 negative x's, so don't do it. You know that it's a negative number to an odd power, so it's going to have lots of pairs and a spare at the end that will make it negative. So this simplifies to negative x to the 9th. You can simplify the negative out. So it's a pretty handy trick. Okay, so this is where we're going to be getting into the graphical portion. So if you're not on graph paper already, please switch. This is Roman numeral 4. Graphing exponential functions. Okay, the generic form of an exponential function is y equals a times b to the power of x. In this formula, the a is what we call the initial value. It's whatever happens at x equals 0, because if x equals 0, b to the 0 is 1, you always get a. So a is the initial value. Now, as far as like the type of exponential, if your b value is greater than 1, so if it's 2, 3, 1.5, anything greater than 1, this is an exponential growth function, which means as x gets big, y gets big. And it happens really, really fast, which is why we call them exponentials. Okay, if your b value is less than 1, if it's 1/2 or 3/4 or 0.8, this is an exponential decay function, which means as x gets larger, y gets smaller, y goes down. So those are the two categories of exponential functions. Now, for both those categories, when you graph it, there is a horizontal asymptote. Asymptote has a P, it's silent in it. And this is at y equals 0 for both of these. An asymptote is an invisible line that your graph gets infinitely closer to. So typically, if it's a horizontal line, your graph's going to kind of get flat. It'll never cross the asymptote, but it'll get so close to it, it's practically the asymptote, just barely off of it. So that gives you your flat part. Okay, so grab your ruler, and over here on the side, you can make this kind of narrow because exponentials get tall really fast. We're going to number these so we don't have to number the points. With exponentials, there's usually not enough space to number the points, so you end up numbering the grid itself. So 1, 2, 3, 4, 5. 1, 2, 3 to the right. -1, -3, 2, -3 to the left. Because this is an exponential graph, it automatically has that asymptote. So take your ruler, offset it from the x-axis, draw dashes, and put arrowheads on the end. And then you write the formula y equals 0. That is your horizontal asymptote. Okay, the example we're going to do is y equals 4 to the power of x. So we're going to do an extended H chart. And sometimes you end up calculating values that just aren't reasonable to fit on the graph. So you always do a couple more points than you actually need, and you'll probably not use 2 of them because they just get too big. So typically you always want to do 0. And I always tell people do 1 and 2, -1 and -2. And again, you have the option of not using all of those. Okay, so if x is 0, y equals 4 to the 0, and anything to the 0 is 1. So our initial value is 1, which makes sense because there wasn't a number in front of that 4. Okay, now 1. 4 to the 1 is 4. Now 2. 4 squared is 16. Now here's where the new stuff comes in. 4 to the -1 is 1 over 4 to the +1, which is 1/4. If you're doing this right, your negative exponent should be a fraction. So if you don't get any fractions, you're doing something wrong. You've got to get at least a couple fractions. Let's do the -2. 4 to the -2 is 1 over 4 to the +2, which is 1/16. Okay, so let's plot these points. 0, 1, 1, 4. Now, 2/16 is heckin' gone, so I'm not going to actually use the 2 and the 16. I got 2 here on the positive end. That's good. So -1 and 1/4, it's kind of shoved in there. -2 and 1/16 is so close, it's practically sitting on the axis. But because of the asymptote, it never actually touches the axis. It gets infinitely close. So this part of your curve is practically flat. And then the curve gets gradually steeper. It never actually goes vertical. It just gets really, really steep. All right, that is an exponential growth curve. An example of exponential curve in real life would be bunnies. A pair of bunnies have at least 4 bunnies. Each of those bunnies have at least 4 bunnies, and soon you've got bunnies, bunnies, more bunnies. So yes, if you don't take care of your bunny issue, you will have thousands of bunnies within a year because they breed really fast. So that would be exponential. Another type of exponential would be infectious disease. If one sick person gets 3 people sick, and then each of them gets 3 people sick. In 2 generations of the virus, you've got 9 people sick. From there, it's going to be 9 times, you're going to have 27 people sick. And then it just keeps growing. So this one's interesting. I got this slide before COVID. But now that we've had COVID, we really get the idea of exponential growth when it comes to virus spreading. Spreads really fast. So that is exponential growth. Okay, we are going to do one more of these, and this one, example 2, is decay. Y equals 1/2 to the power of x. I can tell it's decay because the base number is a fraction less than 1. Okay, so over on the right-hand side, draw the exact same size of graph. And again, we're going to number it. 1, 2, 3, 4, 5. 1, 2, 3, -1, -2, -3. This is an exponential function. You can tell because x is in the powers position. So use your ruler, offset it just a little so you can actually see your dashes. If you can't see your dashes, you need to offset it a little bit more. And label the equation with a box around it at one end, y equals 0. All right, we're going to make another extended H chart. And again, we can start with 0 and then do a 1 and a 2 and then do a -1 and a -2, and we will feel free to skip a couple of those if we need to. Okay, so here we go. 0 first. 1/2 to the power of 0. Anything to the power of 0 is 1. Okay, now to the power of 1. 1/2 to the power of 1 is 1/2. Now 2. 1/2 squared. You're going to need to distribute that 2. So you have a 1 to the 1 times 2, which is 2, over 2 to the 1 times 2, which is 2. 1 times 1 is 1. 2 times 2 is 4. We get a 4th. Okay, now we're going to do the -1. 1/2 to the -1. This is where we're going to use our nifty shortcut. Flip it. 2 over 1. The 1 is now positive because you flipped it. And 2 to the power of 1 is a 2. Pretty nifty shortcut. Let's do the -2. 1/2 to the -2. I'm going to flip it. So I have 2 over 1 now to the positive 2. And now I need to distribute. 2 to the 1 times 2 is 2 squared. 1 to the 1 times 2 is 1 squared, which is 4 over 1, or a 4. So none of these were like outrageously high or outrageously low. If you get down to where it's like 1/32, there's no way you can graph 1/32. 1/16 is about as good as it's going to get for pencil point. All right, let's plot these. Here we go. 0, 1, 1 and 1/2, 2 and 1/4. That's pretty far down there. Now we're going to do -1 up 2, -2 up 4. And just like the growth curve, it gets infinitely close to the asymptote, but never crosses it. So you have a curve that comes down and it gets flatter, flatter, flatter until it's almost totally flat, but not quite. This is a decay curve because as x gets bigger, your y values are coming down. Decay curves don't occur in nature as often as growth curves, but since you guys were from the Tri-Cities, we all know about radioactive decay. So if something has a half-life, let's say you start with 100 atoms, after 5 years, if it has a half-life of 5 years, you have half as much. In another 5 years, you have half as much. In another 5 years, you have half as much. As you can see, the half as much gets a smaller and smaller increment, which is why this starts looking really flat, because the increment of change gets smaller. That would be a decay curve, exponential decay. In this case, radioactive atoms. They don't specify which one because they're not from Richland. Okay, any questions about decay or growth functions?